In section 18.6, we discussed how a point charge creates an electric field in the space around it. There are also many situations in which an electric field is produced by charges that are spread out over a region rather than by a single point charge. Such an extended collection of charges is called a charge distribution. For example, the electric dipole consists of two electric charges of opposite sign separated by some distance and creates an electric field that is somewhat more complicated than that of a single point charge. The electric field within a parallel plate capacitor is produced by positive charges spread uniformly over one plate and an equal number of negative charges spread over the other plate. As we will see, Gauss's law describes the relationship between a charge distribution and the electric field it produces. This law was formulated by the German mathematician and physicist Carl Friedrich Gauss in the 1800s. We begin by developing a version of Gauss's law that applies only to a point charge, which we will assume to be positive. The electric field lines for a positive point charge radiate outward in all directions from the charge, as we see here. The magnitude E of the electric field at a distance r from the charge is E equals kq divided by r squared. The constant k can be expressed as 1 over 4 pi epsilon 0, where epsilon 0 is the permittivity of free space. With this substitution, the magnitude of the electric field becomes 1 divided by 4 pi epsilon 0 times q divided by r squared. We now place this point charge at the center of an imaginary spherical surface of radius r. Such a hypothetical closed surface is called a Gaussian surface, although in general it need not be spherical. One intuitive way to determine whether a given surface of any shape is closed is to imagine filling it with water. If there is no way to get the water to spill out, no matter which way you tilt it, then it is closed. Another way to think of it is to assess whether it would be airtight. If it would be airtight, then it's closed. Back to our spherical Gaussian surface. Its surface area is given by 4 pi r squared. Therefore, the magnitude of the electric field can be written in terms of this area, or E equals q divided by a epsilon 0. Rearranging, we can write this as EA equals q divided by epsilon 0, which is a special case of Gauss's law. The product EA is called the electric flux and is given by the symbol phi E. This result indicates that, aside from the constant epsilon 0, the electric flux phi E depends only on the charge q within the Gaussian surface and is independent of the radius r of the surface. The equation EA equals q divided by epsilon 0 is the special case of Gauss's law specific to spherically symmetric charge distributions and uniformly charged spheres and shells. It is special because the electric field vector is always parallel to the normal of the Gaussian surface through which it passes. We will now see how to generalize this equation to account for distributions of charges and Gaussian surfaces with arbitrary shapes. Here we show a charge distribution whose net charge is labeled q. The charge distribution is surrounded by a Gaussian surface, that is, an imaginary closed surface. The surface can have any arbitrary shape, it need not be spherical, but it must be closed, no holes of any kind. In general, the direction of the electric field is not necessarily perpendicular to the Gaussian surface. Furthermore, the magnitude of the electric field not be constant on the surface, but can vary from point to point. Let's start by examining a tiny element of the surface with area delta A, and assume that it is small enough so that the electric field lines are all parallel to each other. The dashed line labeled normal is perpendicular to the surface, and the electric field makes an angle phi with respect to this normal direction. To get an intuitive idea of flux, one can think of the area element as a window screen and the electric field as wind. The amount of air that passes through the screen per unit time is analogous to the flux. As the screen turns, the amount of wind that passes through it decreases until it reaches 0 when phi equals 90 degrees. It is maximum when phi equals 0 degrees, or when the screen is perpendicular to the wind. The same goes for the electric flux, and the equation for the flux through one area element is phi E equals E cosine phi times delta A. In other words, we use only the component of E that is perpendicular to the surface element, that is, the component of the electric field that passes through the surface. When phi equals 90 degrees, cosine phi equals 0 and the flux is 0. When phi equals 0 degrees, cosine of 0 degrees equals 1 and the flux is maximum. This result was just the flux for one tiny element of the surface with area delta A. How do we obtain the electric flux through the entire surface? We can divide the entire surface into many tiny sections with area elements delta A1, delta A2, delta A3, and so on. Each section is so small that it is essentially flat, and the electric field is a constant, both in magnitude and direction, over the entire element. The electric flux through any one section is then E cosine phi times delta A, as we just determined. The electric flux, phi E, that passes through the entire Gaussian surface is the sum of all of these individual fluxes. Or phi E equals E1 cosine phi 1 times delta A1 plus E2 cosine phi 2 times delta A2 plus E3 cosine phi 3 delta A3, and so on. And this is equal to the sum of all of the components E cosine phi delta A. Now that we have an expression for the total flux through an arbitrary Gaussian surface with an arbitrary charge distribution, we can write the general form of Gauss's law as follows. The electric flux phi E through a Gaussian surface is equal to the net charge Q enclosed by the surface divided by epsilon 0, the permittivity of free space. This is expressed mathematically as phi E equals the sum of E cosine phi delta A, which equals to Q divided by epsilon 0. It says that the total electric flux is equal to the sum of all of the fluxes through the individual area elements. This, in turn, is equal to the net charge enclosed by the surface divided by epsilon 0. Finally, the SI unit of electric flux is Newton times meter squared divided by Coulomb.